Hi year 8, this is a whistle-stop tour of Chemistry Topic 7 Periodic Table. This is the first chapter that you'll need to study for your end of year assessment. The second chapter is chapter 8. So the first thing I'm going to ask you to learn about is and test you on is periods. So make sure you know that periods run across from left to right. In the periodic table, they are the rows, and the modern day periodic table has them going up in increasing proton numbers. So the proton number is actually the smaller number that you actually have on the periodic table. So you've got 19, 20, 21, 22. So all these elements are in order of proton number, and they go up in increasing proton number. The second fact that I need you to understand is that they are all arranged in groups. So elements with similar physical and chemical properties, like the alkali earth metals, which are the second group over here, they all behave in very similar ways, both physically and chemically. So hydrogen over here is actually a gas. So an even more modern version of the periodic table is here. This is the same one as you get in your GCSE exam. And the key over here just tells you what the different numbers are. So the top number over here is the atomic number. Bottom number over here is the relative atomic mass. You can see that modern day periodic tables have hydrogen right in the middle over here. This is because it's a gas, okay? And you've got this little staircase over here. So everything pretty much on the left-hand side over here, everything here are metallic. So we've got the reactive metals, which are this block over here, the other metals over here, and then on the top over here you've got non-metals, you've got the halogens over here, and you've got the inner gases, the noble gases here. So you've got the group numbers, which are at the top over here. In your GCSE as well, you'll have to know what these group numbers are, but you'll need to also be able to say that they are these numbers, which are the Roman numerals ones. So I'm going to ask you to pause the video with each of these blocks. So you need to read this and you need to understand. Okay, so pause the video for that bit. Now pause the video for this bit. This is talking about the first two columns. So these are the reactive metals. Pause the video. Okay, and pause the video for this bit over here. These are the other metals. Okay, and pause the video over here. These are the non-metals above the thick line. Okay, and pause the video over here so that you know what these are. These noble gases. Okay, sometimes called group 0. And pause the video for the halogens. Okay. So what you need to also understand is that sometimes atoms are represented by this symbol over here, where you actually have the element symbol, and then what you'll have is you have a large number and then a small number. The small number is equal to the number of protons in that atom. It's the atomic number. Now that atomic number can be gotten from the periodic table. That number of protons is also equal to the number of electrons. The larger number for an atom is the number of protons in that atom added to the number of neutrons. So to work out the number of neutrons, you get the larger number and you subtract the smaller number from the larger number to work out the number of neutrons. To work out the number of protons, you just see what the atomic number is. And to work out the number of electrons, that is also the atomic number. So historically, there were scientists in the past that discovered that helped to contribute to our modern day periodic table. So this is about Dobereiner triads, and this was around about 1829, and he figured that some of the elements could be grouped in threes. So these triads, tri means three, like a triangle. So these triads worked very, very well for many of the elements, but when they discovered new elements, they didn't fit into the Dobereiner's triads way of grouping, so his ideas after that were not accepted. Then Newland came along, with his pattern. Every eighth element seemed to have similar properties. So there's the first element over here, lithium, 1, 2, 3, 4, 5, 6, 7, and then the eighth element over here has very, very similar chemical and physical properties. That was around about 1864. That's John Newland's octaves. Okay, Newland's octaves. Octaves is same as you find on a piano. So there were problems. Hydrogen didn't fit, and also what he had to sometimes do was he had to sometimes cram two elements in a block over here. It just didn't work. Mendeleev, so Newland actually grouped them in order of increasing atomic mass. Mendeleev also ordered his elements in atomic mass as well, but he got the closest to the modern day periodic table that we can see these days, and his key decision was that where there were gaps, he left them, and he was so confident about his ideas that he said these elements are actually going to be discovered. You'll be able to put them in there. The discovery of germanium in 1886 was found to be very, very close to what Mendeleev predicted, so the scientific community started to accept those ideas. Okay, and then the last group of elements, because they were so unreactive, they weren't discovered until a very late stage. The last group of elements that were discovered were these noble gases. They weren't included in any of the chemical compounds being studied, but argon was discovered first in 1894, then helium 1895, then neon and xenon were 1898, discovered in those days. So the discovery of a new group really fitted quite nicely in Mendeleev's model, gave his idea full support. Actually, I've just looked up on the internet. That is actually pretty much what Mendeleev's ideas were. That's his version that he presented. Well, actually, in actual fact, he didn't present them. He was ill on the day, so he got a colleague to present them for him. Okay, so that's the first two topics. So the way that Mendeleev had arranged the elements were in atomic masses. However, a key thing to get into your head was that he actually arranged them in the order of atomic number, in order of the number of protons that were inside the atoms of each of these elements. And generally, this actually did lead to an increase in mass, but sometimes you do find patterns in the periodic table that just don't quite fit. For example, argon should be followed by something which has an atomic mass of above 40. Okay. However, what comes after argon is potassium, which is 39. Okay, it doesn't quite fit the pattern. Okay, and the reason why is because the modern day periodic table, which fits everything quite nicely, is actually ordered in terms of the atomic number. Okay, so the atomic number of potassium is 19, the atomic number of argon is 18, and that gives a much better fit. Okay, so sometimes also what we needed to do is we needed to actually swap a couple of elements around in the early periodic tables, and they all were good in the end. Okay, talking very briefly, with the modern day periodic table, you'll actually see that if we just look at this period over here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, what we'll also find patterns going across from left to right. So these are the trends in the boiling points exhibited by these period 2 elements. So we start with lithium, beryllium, boron. You can actually see that they go up and up and up, and then suddenly they're very, very low. Okay, this is below the freezing point of water. That's 0. Okay, these ones over here are increasingly difficult to melt, and then suddenly you've got that, and you'll actually find that pattern with the next period as well. Okay, you find that it increases and then suddenly goes down. The next period increases, suddenly goes down. So you get patterns in the periodic table of physical behaviours, and that actually gives a rise to the word periodicity. Okay, electron arrangement. So to explain the patterns of chemical behaviour, you actually need to look at the subatomic particles. So there are some patterns of electrons that you can fit in. We did this way back in the autumn term. So 2 electrons fit in the inner shell, and then 8 electrons fit in the second shell, and then 8 electrons fit in the third shell, and you only need to understand this for the first 20. So you go 2, and then 8, and then 2. 2, 8, 8, 2 would be the electron structure, the electron configuration of calcium. Okay. So these are some examples of atomic structure diagrams for group 1 metals. So these are the group 1 metals that go down here, and you'll actually find that each of those have one electron on the outside, but that electron is further and further away from the nucleus. In period 2, you have 2 shells. Period 3, you have 3 occupied shells, and in period 4, you have 4 occupied shells. Okay. Note that the protons and the neutrons are well in the center. Okay, so where you actually have electron arrangements that are the same, or you actually very similar, where you have like one electron on the outside for these, for example, you actually find that the pattern of behavior is very, very similar. Okay, this is because the outer shell electrons are the things that help that take part in a chemical reaction. So this is the reason why this group behaves in such a similar way. In such similar ways. Looking at word equations, okay, so you can see that each of these metals in group 1 all form metal hydroxides, and they all form hydrogen, okay. But there is a trend in reactivity as well. So the trends in reactivity are as follows. Where you have metals, if you go lower in the periodic table, the metals increase in reactivity. And the reason behind this is because the outer shell electrons are very, very far away from the nucleus, so they don't feel as much of a pull. They're shielded. They don't see, or feel rather, the protons on the inside, so they don't have that much of a pull. There's also these other electrons that seem to cancel out the increasing number of protons there. So it's easier for these electrons to be lost, and that's what governs their chemical reactivity. So for metals, the pattern of reactivity is that it increases in reactivity as you go down the group. For non-metals, it's actually slightly different. Okay, so for non-metals, you actually find that non-metals grab electrons from where they can, and the electron coming in to something like fluorine would actually be coming in much nearer to the nucleus than for something that's slightly lower. For example, chlorine. So there's fluorine, there's chlorine. Okay. So the electron coming into chlorine would fill and occupy one space over here. The electron over here would occupy one space over here. The fluorine incoming electron would feel more of a pull towards the nucleus than the chlorine. So even though chlorine actually has more protons in, the extra protons that the electron would feel are actually shielded by these electrons in a shell that's closer to the nucleus. So the extra protons are cancelled out. And so it becomes a distance thing. The electron is very, very far away in chlorine compared to the outer shell electron of fluorine, and that's why fluorine wants to grab it and attracts it better, and that's why fluorine's reactivity is much higher. Okay, so fluorine is one of the most reactive non-metal elements, and reactivity decreases as you go down the periodic table, down this group. But reactivity increases as you go up for the non-metals. That only works for the non-metals. So, observations during reactions of water is something that you need to also know about with the group 1 metals. So, pause, make sure that you can see that. You can actually see that you've got potassium and lithium. We've also included the group 2 metals over here. Calcium and magnesium, but you can actually also see that they react in a fairly similar way, and the reason why is because they're in the similar region of reactive metals at the start over here. As the non-metals that we just looked at, the halogens, you can actually see when they're reacting with iron, you have a lower reactivity as you go down the group, because fluorine is at the top, catches fire instantly, and you can read that for yourself, and you can pause the video. Okay, right, so we also found that there are patterns going down a group. So this is actually going down a group. So if I just do that, okay, you can actually see it on your video. You can actually see it going down a group there, and as you go down the group, you can see both the boiling points and the melting points, they seem to increase. So fluorines are down here, then chlorines are up here, bromines are way up here, iodine's up here. Okay, so there's patterns there. So I introduced you word equations and balanced symbol equations at the time as well. So those are the reactions of chlorine with sodium, with magnesium, and with aluminium. So make sure that you know about that. Know the reaction, sodium plus chlorine reacts to form sodium chloride. And that was pretty much it for chapter 7. Our next video is going to talk about chapter 8. Okay, so any questions about that? Just let us know. Let us know before you test, okay? Just in case you haven't got the book, I'll just quickly go through this, okay, so that you're not at a disadvantage, okay? So you can pause it as you wish, okay? So make sure that you read up on this. You're going to have more time when you pause this video, okay, to go through it. All right. I think most of you were finding it a little bit difficult with the spotting patterns part. But just know that there are trends going across the periodic table, and make sure that you know that there are trends going up and down the periodic table in the groups. Okay, so there are trends across periods, and there are trends in the groups. Okay, and make sure that you don't mix up, in a silly way, what a group is. A group is up and down. A period is left to right. Okay. All right. Good luck in revising that. My next video will be on chapter 8.